All right, so first thing I want us to consider when we start our discussion with phase change is, let's say I have a glass of water, and this glass of water has 6 ice cubes, and we have another glass of water. This one only has 2 ice cubes. Okay. I have let these glasses of water sit for a very long time. So they are each individually in thermal equilibrium, and each is, of course, a closed system. So the cups of water and ice are nice and isolated from anything else. So what I want you to discuss with the people around you is, how does the temperature of each system compare? Like TA to TB, what inequality goes there, or is it an equal sign? Ready, set, discuss with the people around you. All right, anybody think they have an idea how the temperatures compare? What do we think? Yeah, Kylie, what do you think? Yeah, very good. Yes, because what is the only temperature where ice and water can exist at the same time? Yeah, 0 degrees Celsius. So if both of these systems have both ice and water, and both of these systems are in thermal equilibrium, the only possible temperature for them to be at is 0 degrees. Okay. So let's start to think about what is different. If they are at these different temperatures, but one has more ice than the other. So we'll start with the kinetic energy per particle, that 3/2 kBt. How do we think that compares between system A and system B? Yes, what do you think? Does the kinetic energy per particle depend on the number of particles? No, it only depends on the temperature, right? So this equation only has T for temperature in it. So here, the kinetic energy per particle would be the same because we'd be at the same temp. Now in A, we would certainly have more particles that are vibrating than in B because there are more ice cubes, but they would have the same kinetic energy per particle. Okay? It is the thermal energy that depends on the number of particles. And I did not tell you how the masses of these compare or volumes. Like, you don't know if there's the same amount of volume of water or anything like that. So right now we actually have no way to compare the thermal energy. We can, of course, make some assumptions that because perhaps A has more ice cubes, there are more particles in A, and then A has more thermal energy. But those are assumptions, not specific concrete things, until I tell you specific masses or specific volumes. So kinetic energy is the same, right? So what's going to be different is the potential energy, which we're going to represent with the letter U. Which of these systems is going to require more heat to turn all of the ice cubes into water? Yeah, what do you think? A, very good. Right, A has more ice cubes, so more things that we have to phase change. So A is going to require more heat to change ice to water. A requires more Q to make the ice go to water. So what that means is A has more negative potential energy. So if I was to draw bar charts for A and B, model the A and B system, this is what they might look like. This first bar that I'm going to draw is going to represent the kinetic energy per particle. I'm not doing thermal energy because we said we can't really tell how that compares without knowing masses or volumes. And we said that the kinetic energy per particle is the same. A is going to have more negative potential energy. So maybe A has a bar of -7, whereas B only has a bar of maybe -3. Now, in terms of like a number line and negative numbers in general, -3 is greater than -7. So that means that B has more potential energy than A. So that is the big difference between those two systems, is the amount of potential energy. And we're going to see today that potential energy is going to depend on phase. So we're going to take a side step for a second and explain why this potential energy is negative. Okay? Remember, with energy, the negatives do mean less than 0. It doesn't mean like backwards or to the left or down. That negative does not mean direction. It truly means a negative number. So you might remember from when we talked about gravitational potential energy that the change in any potential energy, gravitational, spring, what we're going to talk about in a second, electrostatic, is equal to the negative of the work done by the internal force to assemble the system from a 0 point. And I'll go through examples of that. So we'll start with an example we're used to. We'll start with an earth and a ball. Now, we have defined that the potential energy of this ball earth system is 0 when the ball is on the surface of Earth. So we're going to assemble the system by lifting a ball a change in height above the surface. Now, if I'm dealing with the ball earth surface, The internal force is going to be a force that interacts between the ball and the earth, and the only option we have is the force of gravity. So the change in potential energy of the ball-earth system is going to equal the negative of the work done by the force of gravity on the ball. So any work done is the force itself times the displacement, which in this case is change in height, times the cosine of the angle between them. So this ball, to go from the 0 point to this second point, was displaced upwards. And the force of gravity acting on the ball acted downward that entire time. So what should the angle be between the force of gravity and that change in height? Yeah, what do you got, Parker? If I'm being displaced up, but the force of gravity pointed down. Yeah, what do you think? Yeah, it's going to be 180, okay? Because we are in opposite directions. So we have a cosine of 180. So that's going to give me a -1. So the force of gravity is doing negative work as I lift this ball. A negative times a negative is a positive. So the change in potential energy just becomes mg, change in height, a positive change in potential energy, because the internal force did negative work. So that's an example that we are used to. So now let's talk about what's happening at the microscopic level. So at the microscopic level, the force between the particles, you could consider it an intermolecular force, but the generic name for that is the electrostatic force. Or Fe. Okay. This is the force that's responsible for opposite charges attracting and same charges repelling. Right? So convention says that the potential energy between two unlike charges is 0 at infinity. Meaning when the two charges are infinitely far apart, that is our 0 point. That's just something scientists decided hundreds of years ago, and we've stuck with it because it is convention. Much like we called an electron negative many years ago, and just stuck with it, right? A negative does not necessarily mean anything in science. We could have called positive and negative charges blue and red, which is actually what we did with quarks. We started calling them colors and flavors. We arbitrarily named things positive and negative. That's been convention. We say convention is potential energy is 0 between two unlike charges at infinity. So here's a water molecule. And here's another water molecule. Pretend that these are infinitely far apart. Hydrogen side of the water molecule is positive. Oxygen side of the water molecule is negative. We know from middle school science and chemistry that positives and negatives are going to attract. So let's call this A and this B. So there is an electrostatic force by B on A that is attractive, and there is an equal but opposite electrostatic force by A on B that is also attractive. So the change in potential energy is equal to the negative work done to assemble the system. So the assembly of our system would be bringing those two charges closer together. So let's use A as what we're going to figure out the work done on. So the change in electrostatic potential energy, UE, is equal to the negative work done by the electrostatic force on A. So we got negative the electrostatic force. Okay. We are moving these things closer together, a displacement D. Now, thinking about the direction of the force acting on A and the direction of the displacement for A, what is the angle between the force and the displacement? Yeah, what you got, Nick? 0. Yeah, this time it is 0 because they are both in the same direction, kind of downish relative to the page. So that means my change in potential energy is negative electrostatic force times displacement. Right? This negative here is why potential energy is negative. Because the work done to assemble those charges is positive, the change in potential energy is negative. Now, the generic equation for electrostatic potential energy is K Q1 Q2 over R. You don't need to know this, but it might be helpful if you want. Q1 and Q2 are the values of the charges, and R is the distance between them. Bless. So if I was to graph potential energy versus R, right, that negative means I'm in quadrant 4, fun, and my graph looks something like this. So up here, where I have a less negative number, that is where we are going to have more potential energy. Down here, where we are more negative, there is less potential energy. And as we can find it kind of follow the curve, it does make sense why, as we get further apart, we have more potential energy. Now, it is this potential energy that is the main difference between the various phases of matter, solid, liquid, and gas. So, which phase of matter has particles that are very close together? Solid, liquid, or gas? Particles that are very, yeah, solid. So that means solids, right, small r, small distance between, they're going to be down here. Okay? Solids are going to have more negative potential energy or less potential energy. Okay? Which phase of matter is going to have particles that are the farthest apart? What do we think? Which phase of matter is going to have particles that are farthest apart? Yeah, gases. Good. Okay. And then solids, of course, or not solids, liquids are somewhere in the center. So this is why, if we were to graph temperature versus heat, right? If we were to graph temperature versus heat for an ice cube that then turns to water, that then turns to steam, right, we would not see something that looks like this. this shows that the entire time heat is added, the temperature is changing. But as we phase change, the potential energy needs to change. Okay? So phase changes require energy. Right? So during a phase change, that Q is needed because it's causing a change in potential energy. So instead of a straight line as we phase change, we end up with the kind of like step diagram that we're used to. Okay? So that added heat is going into separating the particles, right? And starting to change the intermolecular forces. We're not breaking any bonds during a phase change, but we are changing intermolecular forces by changing that potential energy. So now we're going to go to the sheet of paper you picked up on the way in with A, B, C, D, and E. So this is a phase change diagram for water. I tried to draw it approximately to scale, okay, with slopes and lengths of the plateau sections and things like that. Okay, so we have a temperature versus heat diagram. So what we're going to do is we're going to talk about in detail what is happening during each of the sections. So we're going to talk about what phase of matter there is, what is the heat added doing, what kind of energy is changing, and what equation might we use to help us calculate during that section. So section A, as we go from -50 to 0, what phase of matter are we in during section A? Yeah, Kylie. We are in a solid. Very good. We're in a solid. So the added heat here, according to the graph, is increasing the temperature. Right? That's what the slopey part of A says. So what are some things that are also increasing if we have an increase in temperature? Yeah, we're also going to have an increase in kinetic energy during this point. Kinetic energy per particle. And what else is increasing if we increase the temperature and increase the kinetic energy? Think like large scale. If I increase the kinetic energy of an object, what else am I changing about the object? Yeah, right. I'm also going to increase particle speed. Now, during this section, if I want to calculate or solve for anything, I'm going to use a Q equals M, the C, but I need to make sure that I use the specific heat for the solid state times a change in temperature. Because the specific heat does change as we change state of matter. Okay. So let's talk section B. What state or phase of matter is present during section B? Yeah, what do you got? Very good. We got both solid and liquid. On this side of the graph, we're going to be more solid than liquid. And on this side of the graph, we're going to be more liquid than solid. But there is a little bit of both at the same time. So those initial systems we talked about, A and B, the cups of water, okay, they existed somewhere along that plateau region of B, right, where there was solid and liquid at the same time. Now, is the Q being added changing the temperature here? No, right? So the Q added here is increasing particle separation, aka causing a phase change. When this is occurring, this is when we are increasing our potential energy. Is the kinetic energy changing at all during section B? See head shaking? No, good, right? There's no temperature change. So there's no kinetic energy change. So there's no change in particle speed. To calculate during this section, we're going to use the equation Q equals mL, where L is going to represent a latent heat. We'll talk about that in a second. Section C. What phase or state of matter do we have during section C? Yeah, what you got, Nick? Liquid, very good. Okay. So what is the heat being added doing during this section? Is it separating particles, right? Changing intermolecular forces, or is it increasing temperature? Yeah, Parker. Yeah, we got an increase in temperature, right? Which we saw before means that we're increasing the kinetic energy and increasing the particle speed. And we can calculate with Q equals mc liquid delta T. So during each of these sections, that added heat is either changing the kinetic energy per particle or the potential energy, but not necessarily both at the same time. So Q is either doing one or the other. Now, you might be thinking, well, if the particles are moving faster, doesn't that mean that they are further separated, right? As things heat up, they increase in volume, their density changes, and that is true. Right? But the particle separations or the changes in particle separation that are happening between A and C as these things heat up and move faster is so small compared to the separation that happens in B, we consider it to be negligible. So while there are small changes in potential energies during A and C, they are so small that we ignore them, right? We're simplifying our model, okay? So during section D, what phase of energy, or not phase of energy, phase of matter is existing during section D? Yeah, what you got? Yeah, we got liquid and gas. Okay. Of course, at one end here, we're going to have more liquid. At one end here, we're going to have more gas. And we'll see that we can actually calculate how much of the liquid can convert to gas given a specific heat energy, right? We don't need to have a full and complete phase change. It is possible to not add enough heat only some of our molecules phase change, right? So the Q added here increases particle separation, right? Which causes an increase in potential energy. There is no change in temperature, so there is no change in kinetic energy and no change in particle speed. And to calculate here, we can use Q equals mL. All right, and then last section, but not least, we have the section where we are entirely gas. The Q added is increasing the temperature again. So we have increase in kinetic energy here and an increase in particle speed. And we can calculate with Q equals mc for the gas phase, delta T. So that's what's happening at each of those individual sections. Questions, clarifications before we get on to some analyzing? Yeah, what you think, Scott? We're going to get to that in a second. Other questions? No? Okay, so what I would like you to do is with the people around you, using the graph, rank the specific heat for the solid, the specific heat for the liquid, and the specific heat for the gas. Okay, so think about how can I use a temperature versus heat graph to figure out information about specific heat. Okay? Or you can even think about what specific heat represents and think about it that way. Go ahead and all right, anybody want to volunteer what they're thinking for a ranking? I heard some good discussions, some good features of graphs to mention. Yeah, what you're thinking? So gas is the lowest and solid is the most. Is that right? No, liquid, because you said C. So the specific heat of the gas is less than the specific heat of the solid, is less than the specific heat of the liquid. What did you use to figure that out? Very good. We want to look at the slopes of A, C, and E because if you remember, the slope of this graph, in addition to equaling change in temperature over Q, is equal to 1 over mass times specific heat. The mass of the substance is going to stay the same as we phase change and increase temperature. So our slopes are really going to be giving us information about the specific heat. It is an inverse relationship, so the larger the specific heat, the smaller the slope. So the smallest slope between A, C, and E, where we need to consider specific heats, is C. The steepest slope is E, but just by a little bit. Okay, again, I did try to draw this to scale. All right, so E has, like, in terms of boxes, a rise of 4 and a run of 1, whereas A has a rise of 4 and a run of 2. So they are relatively, okay? Now, again, this graph is to scale for water. So just some fun information, the specific heat for liquid water. And moving forward, when I say water, I do mean the liquid phase, right? If I am meaning the solid phase, I will say ice. If I am meaning the gaseous phase, I will say steam. So just moving forward. So the specific heat for liquid water is 4,200 joules per kilogram degrees Celsius. The specific heat for ice, the solid phase, is 2,090 joules per kilogram, so about half the specific heat. And the C for steam is around 1,990 joules per kilogram degrees Celsius. So the specific heats for ice and steam are similar, which is why the slopes look similar. Okay. So another piece of information that we can see from the graph, other than the slopes of those sections A, C, and E, is we can kind of compare the plateau sections B and D. So looking at that graph, hopefully it is very obvious to you that section D is much larger, much longer than section B. That is something we can see to be true. So I would like you to think with the people around you, what does that tell us? So what does that mean? All right, anybody think they know? What does that tell us? Yeah, what do you think? Very good, exactly. So it takes much more heat to go from liquid to gas, to separate those particles, right? Change those intermolecular forces, than to go from solid to liquid. Okay. So let's get into calculating that Q, getting into the Q equals ml of it all. Okay. So let's talk solid to liquid first. So the amount of energy to phase change is going to depend on, or I should say the amount of energy per kilogram. It's going to depend on the latent heat of fusion. Okay. So sometimes this is represented with an HF. I'm going to represent it with an LF. It is a property of the substance, so it'll change whether we're talking about water or iron or whatever. Okay. The latent heat of fusion for water is 3.34 times 10 to the 5th joules per kilogram. So that tells me that for every kilogram of mass of ice, I need to add 3.34 times 10 to the 5th joules to cause it to phase change. So that's where that Q equals ML comes in. If I want to calculate the total amount of energy to phase change a certain amount of mass, that is what I can do. So the energy I need is equal to the mass times the latent heat of fusion. If I am going from a solid to a liquid, we need to remember that this Q is going to be positive. I'm going to be adding energy to the system. If I'm going from a liquid to a solid the other way, I need to force that Q to be negative. So that is kind of the only annoying part here. It's not like Q equals MC delta T where the positive and negative shows up naturally. Here we do kind of think about what direction am I going, and should this heat be positive or negative? Am I adding heat to the system or removing heat from the system? And then to go from liquid to gas, the amount of energy per kilogram to phase change is going to depend on the latent heat of vaporization, which sometimes gets represented as an HV, or you'll see me represent it as an LV, right? That's latent heat of vaporization. Okay. For water, the latent heat of vaporization is 2.26 times 10 to the 6th joules per kilogram. So for every kilogram of liquid water, I need to add 2.26 times 10 to the 6 joules of energy to phase change it into a gas. Now, these latent heats help explain why section D is so much larger than section B. If I look at these latent heats, the amount of energy per kilogram, these two things right, they vary by about a factor of 10 difference, right? One is 10 to the 5th, the other is 10 to the 6th. So it takes about 10 times more energy to convert liquid to gas for water than solid to liquid, right? So that's why we see that section D is so much larger than section B. Right? I obviously couldn't do exactly to scale because I would have needed like 80 boxes, but I tried. Okay? So again, to calculate the amount of energy exactly, the amount of heat we need to add or subtract to phase change, we would do Q equals MLV. So in general, Q equals ML, and then depending upon the phase change that's occurring, it's either the latent heat of fusion or the latent heat of vaporization. Okay. Of course, if we are going from a liquid to a gas, that is going to require positive heat. We need to add energy to the system. And if we are going from gas to liquid, we need to remove energy from the system. So we will have to force a negative Q. Okay. So now if you flip your graph over, Right? We should have a back, and this back is going to be another way to model phase change. Specifically, we are going to model phase change with bar graphs, just like we did with macroscopic or large-scale energy conservation. We can do the same with small-scale energy conservation. Although we're not really conserving energy here, we are adding it, but still. So in order to kind of fill this out for the entirety without any information to begin with, we need to consider a couple of different things. The first thing we should consider is how does the amount of heat added for the different sections compare, right? Like looking at this graph, I can see that section D needs to add the most heat. So I need to make sure in my bar chart, I'm adding the most energy between C and D. And then C is next, then B, then A, then E. So that's something I'm going to keep in mind. So the Q for D is greater than the Q for C, greater than the Q for B, A, and E. And then I can kind of work backwards. So maybe between C and D, I add 7 bars of energy. Right? That's my most. That's just an arbitrary number I chose. Something that's kind of big. I could add 10, just something I chose. Because this goes from the end of C to the end of D. Okay. And then section C, maybe from the end of B to the end of C, I add 5 bars worth of energy. And then from the end of A to the end of B, maybe I add 4. And then between 0 and A, maybe I add 3. And then between D and E, maybe I add 2. So that's part of why I started at 7, is because I knew I needed at least 5 different amounts of energy changes. And I knew that the change in energy between C and D is pretty big. So I wanted to make sure I had a number larger than, or large enough to kind of make that one a little bit bigger. Okay. Not to scale, but gives me a general idea. So now I want to think about what type of energy is going to be changing. We already kind of did this, right? During section A, we said we had a change in kinetic energy. So from T equals 0 to to the end of A, I'm going to increase my kinetic energy. Then from the end of B, or end of A to end of B, or section B, right, I'm going to increase my potential, UE. And it just kind of alternates as we go. We are either increasing the kinetic energy and the temperature, or we are increasing the potential energy and causing a phase change. So there's a few things I want to consider when I'm making my arbitrary choices. Kinetic energy should not be 0, or kinetic energy per particle should not be 0 for any of these, because that would mean that I'm at absolute 0, and we are not at absolute 0. Okay? So to begin with, I need to start with some kinetic energy. It doesn't have to be a lot, but I do need to start with some kinetic energy, or thermal energy, right, if we want to think bulk scale. Also, potential energy can only be negative. Okay? We talked about why that was the case earlier on. Right? Potential energy can only be negative. So in total, looking at my increases in potential energy, I increase my potential energy by 11 boxes. So I want to make sure that my initial potential energy is negative enough that even adding 11 boxes to it is still negative. So maybe I start with something like negative 12 boxes. 6, 7, 8, 9. Okay, so I have 1 box of kinetic energy, negative 12 of potential, for a grand total energy of negative 11. So between t equals 0 and the end of A, we decided to add 3 boxes worth of energy. And that 3 boxes goes to increasing kinetic. So my kinetic energy needs to go from 1 box to 4. And the changes in potential energy are so small during this section that we ignore them. So I still have negative 12 potential. So now my grand total energy is negative 8. And that makes sense to me because negative 11, my total energy before, plus 3 does in fact give me negative 8. So I've increased my energy by 3. So with the people around you, go ahead and fill in the remainder of the bars, right? With the choices, which were arbitrary, but based in fact that we said. Ready, set, go. All right, so when I go through and do this, this is what my graph ends up looking like. It is a touch messy, but that's okay. We are consistently adding heat to the system, consistently adding Q. So it makes sense that my E total is increasing with every step. So my potential energy is increasing during the phase change, aka getting less negative. My kinetic energy is also increasing with every other step, aka getting more positive. Walking around, I saw most of you had these graphs. Remember that adding a negative bar is just like adding a negative number, which is why for like the end of A, we get 4 plus negative 12 is negative 8. Okay, keep that in mind. Any questions on the bar charts? No? Okay, so for the last bit of class, you guys are, where is it? You picked up a single page worksheet on the way in, which essentially has this phase change graph, but you guys are going to go ahead and calculate each of the individual sections and then actually graph to scale. Okay? The answers are in parentheses. You'll notice the answers are in kilojoules. That was just to make the writing easier. You can answer in joules or kilojoules. Although I do think, yeah, the graph is in kilojoules, so it does maybe make sense to answer in kilojoules. All right, to go from joules to kilojoules, you're just going to divide by 1,000, like going by grams to kilograms. And then there is a question on the back. Any of the specific heats and latent heats are on the top for you that you need because this is for water. All right, ready, set, go.